Good afternoon, good morning, good evening, whatever it is for you. The speaker of today is Dr. Walter Rocchia from Istituto Italiano di Tecnologia in Genova, Italy. And the title of his presentation is going to be Electrostatics Disguised as Hydrophobicity, a new method to probe protein-ligand binding. So Walter graduated cum laude in electronic engineering in 1996 and got his PhD in molecular electronics in 2000. Then he was research scholar at the biochemistry department of the Columbia University in New York City. And in 2003, he joined the molecular biophysics group at Scuola Normale Superiore in Pisa, Italy. In 2008, he joined the drug discovery and development department of the Italian Institute of Technology. And in 2014, he created the Concept Lab and co-founded the Biggie Technologies company. Among his interests are continuum electrostatics modeling of biomolecules and applications of molecular dynamics to molecular recognition and binding. So I will leave the stage to Walter, and then I will moderate the Q&A.
Thank you very much. Okay, tell me if...
I can see your screen.
You can see my screen, also the presentation?
Yep.
Okay, very good. Okay, so I'm very happy and excited to talk today, a bit, yeah, excited. What I'll be talking about today is actually the continuation of previous work that already I presented to the past edition of the Protein Electrostatics. And it goes along the idea of using electrostatic-like bias in molecular dynamics in order to accelerate or to better study the protein-ligand binding events. And so this is, let me see if, okay. So the presentation will be basically divided in two parts. In the first one would be actually, something that some of you may already have seen, where we use an external electrostatic-like bias in order to increase the chances to observe the binding with the correct binding pose of the ligand to its cognate binding site. And while the second one is a much recent work where we try to see whether we manage to implement a bias which is similar to hydrophobicity, again, in order to accelerate the binding and to also to study molecular determinants of the binding itself. Actually, the premises of the presentation of today are quite similar to the presentation of Wei Yang. So the point is that if you want to study some what they are called rare events, some phenomena in molecular dynamics that are not easy to access. When you are studying the accessibility from one state to another, in case there is an energy barrier which is limiting your ability actually to sample the entire conformational space, there are several things you can do with some caution, of course. So the most basic thing you can imagine is plain MD, brute force MD. This has been done by many people. I'd like just to remind the realization several years ago of the Anton supercomputer by David Shaw research, where they actually implemented hardware routines especially for molecular dynamics, in order to accelerate the simulation itself. And of course, the advent of GPUs helped a lot in this sense. So there have been quite a number of studies nowadays where the binding event has been studied by plain molecular dynamics. Still, it's kind of difficult, even in this case, in the extreme case where you have a huge computational power, to get a good statistics that allows you to estimate, for example, binding affinity. And even in this case, for example, some quantity like residence time for a good drug, which can be of the order of seconds or even minutes, is still far from reach of these tools. So a different approach is so-called enhanced sampling, where you try to use basically some tricks in order to accelerate the occurrence of the event you want to see. Of course, if you are using some perturbation or external bias, you are, of course, biasing your simulation. You have to be cautious how to derive unbiased estimates of the observable of your interest. One of the classes of enhanced sampling that one might think of basically start from the definition of a collective variable, which should be an approximation of the reaction coordinate for the event of interest. And once you know this, you can actually accelerate the sampling of this collective variable. And by forcing the sampling of this collective variable, you may try to derive some statistical observables. And the most interesting probably is the free energy, which in my case will be the free energy of binding, but it can be the free energy of the of passing from one to the other state of interest. However, approximating the real reaction coordinate is a very, very difficult thing, especially for realistic processes. We focused on protein-ligand binding, a universal collective variable able to study all or many binding event it doesn't exist. Every system has its own peculiarities, and it's difficult to really find a collective variable which is portable from one system to another. What happens when we are using a wrong or a too degenerate collective variable? For example, the most obvious is the distance between the binding site and the ligand. If you are using a wrong collective variable, you are not actually forcing the correct exploration of the conformational space. And even if you manage to observe something which may resemble what you want to see, the phenomena you want to study, the energetic characterization of this is it will be probably wrong. By the way, in order to observe this, you probably will need to inject a lot of energy into your system, and in this way you will observe high energy paths, which are not the ones which are followed in more realistic cases. So what happened? What we decided several years ago to do in this respect was actually to somehow to abandon the idea of finding the universal collective variable, to accept the fact that if you know the coordinate reaction so well that you are able to get an implementation very, very close to reality, if you would be able in principle to approximate the committer function for the events you want to study, probably you don't need to perform a simulation. You already know what are the relevant degrees of freedom. You probably already know enough of the system in order to modify it and to affect it in the way you want. So we wanted to try to circumvent this problem. And well, in nature, of course, electrostatics is one of the most relevant driving forces for the association process, and which is able actually to increase the K-on for a natural substrate. So we decided on one side to devise an electrostatic bias, which is actually additive to the real force field, which is ruling the interaction between the ligand and the protein. And one of the idea is, since it is still a distance-dependent bias, however, spreading the attraction all over the atoms, the heavy atoms of the ligand and those of the binding site, we thought it could be of help in triggering concerted events in order to observe binding. And in addition to this, in order to devise this bias, you only need to know the atoms which are basically defining your binding site, which in many cases is they are known. You know where your binding site is. If you have some more specific knowledge, it's easy also to introduce in this kind of binding, because you can put some specific attraction between, for example, two atoms that you know that they will get in contact after binding. So you can actually input some data from experiments into this protocol. So this is the shape of the bias is actually very simple. Is resembling the bihookel interaction, so a decay electrostatic interaction with a decay function. But the constant, the modulus of the force, is actually modified in order to make it adaptive from several respects. First of all, there is always a fixed ratio between the overall intensity of the force acting on the ligand with respect to the one that a natural system would apply to the ligand itself. So you always compare what the regular force field would say in terms of intensity with what you are applying. So you can never be too strong in the bias you are applying. Second, you can input in your system what we call a switch-off residue, which you can make different trials, or you can use your chemical intuition in order to identify a residue which should correspond to the transition state of the binding process. So you can imagine then when the ligand gets in contact with this residue, the hardest part has already been passed, and the following evolution will be easy. So the ligand will be able to feel the actual forces from the final part of the binding site, and it will go down the cliff. Third adaptivity is in terms of a memory effect. Once the modulus of the bias started decreasing, it can never increase again. So the sum of these ideas is basically, on one side, to reduce the maximum intensity that the bias can apply to the system. On the other side is it wants to avoid the possibility that in order to force the entrance, you are going to destroy some structure to create configurations which are really unlikely. So it's better to prefer that the ligand doesn't enter rather than forcing it too much into entering the binding site. Of course, the price you have to pay is that you reduce the likelihood to observe your ligand inside the binding site. And in this case, what you need to do is to make several replicas in order to see whether you are lucky in some of them. So the basic protocol function in the following way. We use NanoShaper, which is the tool we devise in order to build the molecular surface and also to identify pockets. We use this in order to identify the pocket which is corresponding to the binding site of our interest. NanoShaper is also able to identify the entrances of a given pocket, and then to have the average normal to each of them. And at a given distance, we can position a ligand, a copy of the ligand, at some distance from the entrance of the pocket. So we can start, as you can see here. So the case we took is the interaction between the SAR kinase and PP1. Why we choose this system? Well, kinases are very important, but the reason for this was that at that time, D-Show released a work and the corresponding simulations where they were studying by brute force molecular dynamics the binding of PP1 to SAR kinase. So we wanted to see whether we were able to see similar or different things from the plane molecular dynamics, and to see whether we were able to observe a correct binding in a shorter time. What was observed in the work of David Shaw was that in their cases, they observed, I think, 3 binding events, and they took on average 117 microseconds in order to observe them. So as you can see here, the ligand is approaching the binding site. In the graph, in the upper plot, you have the RMSD. In the lower plot, you see the modulus of the bias, so the bias entity. Now, as you can see, the ligand is getting closer to the red residue, which is our switch-off residue. And as soon as it gets close to it, the modulus goes to 0. If the modulus goes to 0, it can no longer recover. So from this time on, the following molecular dynamics will be just plain molecular dynamics, so we can make statistics, reliable statistics out of it. So we perform 20 run per pocket entrance. So in this case, there was only 1 entrance, so only 20 runs. Every run is 20 nanoseconds long. So several things can occur. In many cases, the ligand doesn't enter because there is some obstacle, and as I told you, we don't want to push it too strongly in order to get into the binding site. In some cases, however, the ligand gets close enough to the switch-off residue, and so it is able to enter, to bring the modulus to 0. So we have a limited number of trajectories which end with an unbiased part. We took them, so we discard completely the others. We took just the plain molecular dynamic pieces deriving from this campaign, and which occur on average in our experience in the 5% of the replicas. And we now have to do something in order to identify which observed pose among them is the best one. And in order to do this, we use, okay, in the meanwhile, the binding, as you have seen, has been found. This was one of the best trajectories for, bias trajectories for this system. In less than 20 nanoseconds, we got an X-ray, an RMSD from the X-ray of 1 Armstrong. So how do we choose among all the relative conformation observed during the molecular dynamics, the plain molecular dynamics part, which could be the most reliable one? So we do some clustering. We put this chunk of trajectories together, and we do some clustering in order to get 20 representative of the most frequently occurring and diverse poses. And we post-process those poses with a scale MD. So in scale MD, you are just putting a coefficient below than 1 in front of your potential energy. And so you are actually weakening all the interaction of your system, present in your system. And by doing a very short, less than 5 nanosecond run of this scale MD, you will see things, crumbling, and let's say all the interaction are weakened. In order to evaluate which of these ligands, which of these poses is the most reliable one, we observe the scale MD trajectory where the RMSD is more stable. So we compare this. So this is not as fast as, of course, a scoring function, but we observe that the performance in terms of the capability to say that the most stable, RMSD correspond to the best pose is pretty high. So the performance in terms of capability of identification of the best pose is better than the classical scoring function that we use for comparison. In order, in addition to this, you can run several of them in a trivially parallel way, so you're not really spending a lot of time in this. So this is the table with the basic results. We apply this protocol to many drugs or candidate drugs in realistic targets. And what is interesting to observe here is not just the third column where we have actually the best, the chosen medoid RMSD with respect to the crystal, which you can see is pretty good in almost all of the cases. Of course, the minimum observed RMSD along the trajectories is lower, but we don't know how to pick this. So we only have to use as our benchmark the third column. And another thing which is interesting is the fact that from the point of view of computational cost is much more convenient with respect to any plane MD you may imagine. We have 3 cases where we can compare with plane MD. One is GPCR beta 2 against alpranolol, which again was done by the show, SARC against PP1, which is the one that I've been talking about, and one of PMP against an inhibitor, from which we already did some work, and we used the GPUs in order to perform kind of long simulations. All of them actually were done in presence of many ligands. And so you have also to pay attention to the fact that these many ligands in some cases may interfere with each other during binding. And you have to pay attention to this. So the first message is in these cases we were able to find a final pose which was pretty close to the crystal one. Second aspect we wanted to consider was, so what about the path? How different or how similar is the path that we observed in our biased simulation if compared to the one of the only ground truth we can have, which is the plain molecular dynamics simulation from the show. In this case, what we can say is that in all of the cases, we have 2 of our simulation and 1 which is our reference. We observed that irrespective of the starting location, all of the ligands before entering, while there would be space for entering from the side of the main entrance of the site, all of them pass through the same place where we discovered a posteriori there is an hydrophobic patch at this part of the site, of the entrance of the site. So what we can say is that there are some similarities we can draw from our comparison between the accelerated trajectory and the plane one. So conclusion of part 1. In this approach, we seem to be able to accelerate the protein ligand recognition and avoiding too strange or highly unphysical trajectories. And we use redundancy in order to compensate for the lack of accuracy of our collective variables. So by no means I'm saying that, I will repeat at the end of the talk, that this collective variable can be a good collective variable for traditional application of enhanced sampling. So you can, for example, use metadynamics in order to devise, in order to build a free energy landscape. What you can do, however, is to take the path that you got, that you know is good in case you have the crystal and you know that the final conformation is right. You can use that path, and you can use some of the already existing approaches that try to evaluate the free energy along a path. And in that case, you can use, for example, metadynamics or other approaches to try to build a free energy landscape out of this. Okay, let's now switch to the newest stuff. So the idea was, okay, we know that electrostatic and hydrophobicity are the main determinants of molecular recognition and binding. We thought that with electrostatic we did quite a good job. Can we try to do similar thing with hydrophobicity? Of course, hydrophobicity is way more difficult. First of all, just the first thing that comes to my mind is that it's not pairwise. There are a zillion of papers discussing about hydrophobicity and the effect of hydrophobicity on cavity ligand or protein-ligand interaction. You can broadly probably divide them in two classes. In one of them, you really talk about the general concept of hydrophobicity, and you build some kind of an idealized system, and then like a host-guest situation, and you study the effect of tweaking with hydrophobicity and observing how the host-guest interaction reacts. And on the opposite side, and this is, I would say, a more physical approach. On the opposite side, there is more of a chemical approach where you consider the explicit interaction between the chemical groups and water molecules. You want to evaluate the energetic convenience for a water molecule to be in the binding site rather than being expelled out of the binding site. And you want to, for example, when you do drug design, you would like to explore different decoration of your ligand in order to see whether one of them is able to take place, to replace a water molecule which was unhappy to be there, because so it was it was energetically unfavorable to be there. And so we want to see whether it may make sense somehow to mix the two approaches, to keep the ability to tune hydrophobicity in the physical sense, but to apply this thing, this idea, also when we were studying a realistic system, such as a drug interacting with its target. And we go back to our friend Stark against PPI so the system, still the study system is the same. The bias that we apply is different. So the very basic idea is, okay, let's say the ligand and the binding site become a little less hydrophilic than they were at the beginning in the regular case. How can we practically apply this? Okay, we can apply a repulsive bias, where the heavy atom of the ligand and the heavy atom of the binding site actually repel the oxygen atom of the water molecules in the surrounding. And this is what we did. And we can use the very same collective variable we did before. So we can actually apply a contrived external electric field. Very weak, again, the idea is not to perturb the system too much. We fix the hydration that we aim for. So we start from a reference molecular dynamics. We evaluate the electrostatic and the fictitious electrostatic energy of our ligand interacting with surrounding water molecules and of our binding sites interacting with surrounding water molecules. And then starting from these references, we say, okay, we want to bring the hydration from the original 100% of reference to a target, which will be 80%, for example, or 50%. And we see what happened. This is what we did in this figure. I hope they are clearly represented what we are trying to do, and what we observe actually. Okay, first let me explain a little bit about the protocols. We tried 3 different protocols. One we call, of course, we have the reference, which is the unbiased case. Then one which is the single bias, so only the ligand repels water. And so we bring the hydration from the initial value to its 50%. Then we have the double bias, where we dehydrate, let's say, both the ligand and the binding site. The target for the ligand is 50% of the original, and for the binding site is the 80% of the original hydration. And then we tried to do something more, a little more elaborate. At the beginning, we dehydrate the ligand, and then from at some point, we also we further dehydrate the ligand, and we also start dehydrating the binding site. The length of each simulation overall is 35 nanoseconds. And usually a lot of replicas are needed in order to observe some successful event. We tried 64 runs per protocol. In the case of double delayed, a little bit more. And here are the results. First of all, as we expected, the bias keeps the ligand always close to the protein. This doesn't mean that this leads necessarily to a favorable binding event, but nevertheless, it never goes away. So if you consider the distribution of this RMSD, in the case of unbiased, you have a kind of spread distribution. Some of them go very far away, some others stay at some distance. Of course, you never observe binding. If you apply a single bias, the distribution is reasonably closer to the protein surface, but still we observe no near native configuration in 35 nanoseconds. If we apply the double bias, so we dehydrate the ligand and slightly dehydrate also the binding site, we observe one positive case of binding. With an average RMSD of the last 1 nanosecond of the simulation of 0.67 angstrom. And in the case of the double delayed, we observe 3 near native conformation, but a lot of unphysical path. And so we have the impression that the bias we are applying in this case is too intense. And so we actually, what we like most is the double bias part. Okay, so is this just a fake way, or are we really mimicking hydrophobicity or not? So it's hard to say. one of the things that are known about how hydrophobicity works is that, of course, we apply this is the hydration of the binding site before the ligand get close to it. So this is somehow, we are only considering the binding site and surrounding water molecules. And as expected, the density of waters is smaller than in the unbiased case. What is similar to what is expected to occur near hydrophobic surfaces is that the standard deviation, the fluctuations of the water molecule, the density of water molecule around the entrance of the binding site is increasing in the case of the bias. So this is not definitive, but is promising in the sense that some of the observable that are that people connect to the concept of hydrophobicity we observe also after the application of this bias. Then what we did was the comparison with the plain MD from the show research. In the left column, we have the data from the the successful trajectory from the Anton supercomputer, and the time unit is microsecond, while on the right we have our simulation, and the time is in nanoseconds. First of all, the hydration of the binding site, and we see that the numbers are comparable. The behavior is similar. In the central row, we have the hydration of the ligand, and the final part of in the final part that we observe similar value again. And here we consider actually two phenomena, two molecular determinants that we that came up to our observation, and they are the presence of two salt bridges, lysine against an aspartic acid and against the glutamate, and we compared the hydration of the lysine with the occurrence of those salt bridges, and how these salt bridges, especially the first one, behave during the binding. And this is kind of interesting. Of course, this is kind of intuitive. There is a correlation between the breakage of the salt bridges and the hydration of the lysine, as expected. So let's focus on what we call the KD bridge. So let's first say that for people, I'm not an expert of kinases. For people who are experts of kinase, the KE bridge is extremely well known, extremely conserved. This is basic of everybody studying kinases. KD is still very conserved, as we will see, but not as known as the other one. We actually focused on this. So this is the plot of the distance between the ligand and the binding site. And the images here correspond to this first part before the breaking of the KD salt bridge, and in the end, when also the KE breaks. Correspondingly, the pocket, the binding site, increase a little bit its volume and change shape. So the idea, so the original idea was, okay, it's intuitive that in order to enter, in order for the ligand to enter the binding site, if there are water molecules in the binding site, which some of them there will be for sure, otherwise most likely the site will collapse, they must go away. But then what we realized is that dehydration is not is more subtle than one might think of, and the case of this salt bridge is actually very critical in this sense. So the salt bridge, if you dehydrate too much the KD salt bridge, you are actually stabilizing this. But what we observed is that upon binding, when the ligand entered the binding site, this bridge is broken. And with this, so we asked for help some colleagues from the Institute of Cancer Research in London. They are experts of kinases and proteins involved in cancer. And in order to, so they know a lot more about we do about the structural biology of kinases. And so we did some more structural bioinformatics analysis. So what we found out is that, okay, both lysine 295 and aspartate 404, they are very much conserved individually in the kinase superfamily. But what, so by doing some down selection from the, thanks to the cancer resource at the London Institute, so we go from the protein kinase superfamily to them for which is available 3D structure, and then from those where the 3D structure include the catalytic domain and include the where the lysine and aspartate are actually sold. And then we want to see whether these residues are are making a salt bridge or not. And actually, what happens is, what seems to be true is that, so the salt bridge per se is a pretty conserved feature, and in some cases the bridge is formed even after binding of the drug of inhibitor. In some cases, you may imagine that the bridge is reforming after the binding occurred. In many cases, you can say that breaking the bridge is necessary for many ligands, for many inhibitors to bind to the binding site. And this is a consideration we go out in this direction. So one of the drug-resistant mutation in the case of SARC is the threonine to methionine mutation. And so we are replacing a more hydrophilic residue with a more hydrophobic one. If we do a simulation of this system in the two cases, after some time of relaxation, we observe, well, of course, as expected, if you want, that the degree of hydration of the binding site is lower after mutation. And correspondingly, that the stability of the KD bridge is increased. And this might be, for the time being, this is an hypothesis. This might be a reason for, let's say, making the site less permissive to the binding of inhibitors. Okay, so this is one thing. After the conclusion, I will give you something very, very recent. So the conclusion on this is that it seems that the trick we did in order to mimic hydrophobicity by using electrostatic repulsion with respect to water seems to be successful and seems to be able to mix the chemical and the physical viewpoints, enabling the possibility to study a variable, a smooth change in hydrophobicity without the need of making a mutation, but just exploring preliminary what might be the effect of some mutation going in some direction. So this could be an interesting tool, I hope, for the community. And the application of this bias increases the chances to observe binding without specific information about the system. I started the talk saying that if you know everything about your system, you probably don't need to make a simulation. So we want to have something which is, if you want, quick and dirty. it should give some answer in a reasonably short amount of time and with reasonably limited computational resources. So giving more intuition to people who are doing, for example, drug design, in order to improve their molecule or to understand a physical process. In order, if we are using as a figure of merit the increment of chances to observe the right binding, this is not the hydrophobicity trick, let's say, is not as effective as the first tool I showed you. But the first tool is more, if you want, it's more tuned around the system, while this is more general. The nice thing of this approach is that, as I showed you, the bias is a semi-parabolic shape, has a semi-parabolic shape. So when the hydration go below the threshold that we fixed, for the rest of the time, again, the simulation is unbiased. There is no, the bias switches off automatically, intrinsically, if you want. So in the end, I kind of like the idea of being able to tweak both electrostatics and, if you want, hydrophobicity during a simulation, an MD simulation. And I want to stress that neither the first one nor the second one of the collective variable I've shown can be considered a sufficiently good approximation of the binding reaction coordinate that could be alone used for free energy calculation.
So I'll ask you a question, Walter, on the first part, which of course is a naive question, which is that in the early 1990s, some people may recall Marilyn might, Kim Sharp, Anthony Nichols and colleagues talked about shape-dependent hydrophobicity and some sort of massive coming together of all the different theories and the different scales. And I want, if I understand your biased interaction between water molecules and some parts of solutes, to quote your paper, is that effectively giving, I mean, it's doing many things, but is it effectively giving something like a shape-dependent hydrophobicity, where you have a more enclosed water molecule that interacts with a larger number of solute atoms, and therefore, in principle, there's a larger bias there? I don't know. It's a very unthought out question.
Wow. We didn't look at this aspect. So basically, we first define a set of atoms, and then all of the water molecules which are within some distance from each of them, they feel this repulsion in a collective way. By collective, I mean that you apply the bias to electrostatic energy of the interaction. So some of them, so the constraint is on the sum of the individual pairwise interactions. We didn't look at the correlation between the shape of the region we are dehydrating and the whether there is some focusing of this shape of this effect or not. So it's a very interesting. I thank you for this suggestion. It would be kind of difficult to make a thorough description of this, but it's very interesting, again, to go together with the both chemical and physical viewpoints. Thank you.
Thank you.
Olivier Binucolo, I hope that's the correct pronunciation.
Yes, it's right. Thank you. Thank you for giving me the word. Thank you also, Walter, for the very interesting talk. I really liked this idea of biasing the hydration with this bias. And I wanted to ask you if you think of a way to also consider the diffusivity of water, because this also plays a role in the interaction between the ligand and the protein. And do you think of a way to extend your method to consider also this?
Well, I think so. probably changing the diffusivity is would be more difficult than what we are trying. Now we have somehow a tool which is enabling us to build up this fictitious energy and electrostatic energy, if you want, which go in addition to the regular interaction. And so we can tune, so we can increase or reduce the intensity. We can change the philosophy of which we apply the bias, or we can apply different bias to different pairs of atoms. And interestingly enough, only them feel the bias. So all the rest of the system is completely blind to this. Mm-hmm. So and I would say also that it's easier to handle forces in molecular dynamics than handling. So changing diffusivity will involve a completely different mindset. Also technically it would be more difficult. So
sorry, it was not changing the diffusivity parameters. It was more the idea, more or less what you say, that you would progressively change the hydration. This is also an indirect way to consider the diffusivity.
Okay. Yes. Yeah. Okay. So sorry.
Otherwise, it's much too complicated.
No. Yeah. Okay. We kind of we try to see whether the behavior of water molecules was not too much different from the biased and the unbiased case. We did a comparison. And actually, we observed that the diffusivity, let's say the fluctuations are increasing. So there is a larger amount of fluctuations both around the ligand and around the dehydrated binding site. We didn't perform any more detailed calculation, probably also because this would have required a lot of more of replicas in order to derive some statistically meaningful or thermodynamic quantities. But with the fluctuation increase, this is for sure. You're welcome.
Okay, Antonio Bautista.
Okay. Well, thank you for the really nice presentation, Walter. I have a question which is a kind of a bit philosophical, maybe, which is related with the hydrophobicity, because it's interesting. Because in a sense, what you are trying to do is to, in a sense, to decrease the hydrophilicity of the molecules, right? Of the molecules you know to be hydrophobic, correct? Yeah. So this reminds me, I don't remember this so well, but because I looked at this a long time ago, but I know there are cases, and you can measure these. I mean, if you can measure these using Kirkwood-Buff theory, I think. You can measure this experimentally. There are cases where you have this really interesting situation where, suppose you have a solid, okay? You can measure that solid may like water more than the other molecules of its own kind. And yet, when you put a bunch of those molecules in water, well, the water doesn't like them, so they behave they form an hydrophobic droplet, even though they prefer the water. I mean, in terms of the Kirkwood-Buff parameters. So it's really interesting because, in a sense, as I said, I don't remember this so well. Okay, I looked at this, I don't know, 10, 15 years ago, maybe last time, but it's quite interesting because at least in some cases, and I mean, this may be completely relevant for the situations you are describing here, because as far as I remember, these experiments were done with really very small molecules, and in some cases, I think with rare gases and stuff like that. But in principle, it is possible that the molecule prefers water, but still goes to interact with something else because water doesn't like it. This is a bit counterintuitive, isn't it? But when you were presenting the way you dealt with it, I suddenly remember this case.
Well, what I can tell you is that if we do not apply any bias, the ligand goes away pretty easily.
Oh, sure.
These are 35 nanoseconds long trajectories. There is no way that the ligands has time to get in touch with the binding site. If we dehydrate only the ligand, also because we always try not to act too strongly, it somehow it gets closer to the surface. It doesn't stick to it. So we did not observe actual contact between the ligand, but the ligand somehow gets in vicinity of the surface, probably because at that distance it managed to fulfill the requirement of 50% of hydration, average hydration, and still it rolls over the surface. So probably if we would increase the length of the trajectories, eventually some of them may finally get into the binding site. Right. So in terms of preference, so yeah, I would say that the behavior is well, in many cases is as we would have expected, intuitive. I mean, more naively.
Sure. Oh yeah, absolutely.
Yeah. Maybe it would be nice to, if there is some specific system where some specific behavior is pointed out, maybe it would be nice to simulate this to see whether we can reproduce this data.
Yeah, I can try if I can find an example of this. I don't remember where I read it. Yeah. Okay. Yeah. Thank you. Very interesting.
Thank you.
Thank you. I don't know if there are any more questions. I don't really see any questions in the chat or any raised hands. If there aren't any, maybe Walter would like to add some final remarks.
Okay. Well, I'd like to thank all of you for being here and listen to me. So next week there will be one short talk by Nicoletta Liguori and one regular talk by Guo Weiwei. And well, for those of you who are not present at the beginning of the meeting of today, with Wei Yang, we will be co-editing a special issue dedicated to protein electrostatics on the Journal of Physical Chemistry B. So I would be encouraging all of you to of course, to present their work and to make it a very nice issue. Okay, thank you very much.
I would just like to say that Miguel Machupero just wrote in the chat that now we have 91 subscribers. So
thank you. Thank you.
Yeah, so share the YouTube link with your labs, your communities, send it on your just spam it around so we can get it. Yeah, okay.
Okay. Thanks a lot. Okay.
Thanks. Thank you, Walter.
Thank you, Marilyn. Bye-bye.
See you next week.